Okay, are we good to go?
Yeah, we're good to go.
I'm Brad Fitzpatrick. I work on Go. I work on standard library. And anyone here use net HTTP? Okay. This is more net HTTP stuff. This talk is, I guess, maybe 1/3 about HTTP2 and what it is. I'll go really quickly on that, and then we'll jump in and look at lots of code. So yeah, I work on HTTP and standard library stuff. So yeah, HTTP2, a little history of typing some stuff in a thing and getting a document back on the internets. I got to start with Gopher because it's Gopher. The protocol kind of looked like this. The red was kind of what your browser or whatever you called the thing that was a Gopher browser sends, and the response was like lists of text, and there were columns, and the little 1 and 0 basically were the content type, whether it was a text document or another listing, or the like 7 meant it was like an audio file or something. Then HTTP 0.9, like 91, you basically just sent one line. There were no content types really. Everything was, I guess, HTML. 1.0 started adding some headers. You could send some key value pairs on your request and get some key value pairs in your response. You have different content types. It evolved kind of slowly. They added a keep alive, so you could opt in to like not tearing down your TCP connection every time. And on the response, the server would say, OK, this is a keep alive. And then on the same TCP connection, you could then issue another one. In 1.1, that was implicit. So all connections are keep alive unless you opt out of it and say connection close. Now you have to say what host name you're talking to make, solve the IPv4 shortage problem and make virtual hosting easier, that you could have virtual hosts that have one IP address for hundreds of customers, and you could load balance differently. So now we're in like 99. And that's about it. That's about where we are. So recently, this is HTTP2 request. It looks a little bit different. The main thing you'll notice is, for the last, I don't know, many years, it was text protocol. You can only do one thing at a time. Your browser could only be asking for a single request at a time. And if you're hundreds of milliseconds away from your thing, that was basically like 600 milliseconds of dead time that the TCP connection was there. It has accumulated lots of hacks and stuff, like special cases for working around browsers and weird servers and stuff over time. HTTP2, on the other hand, is still pretty clean and consistent because there's not many implementations and people are trying pretty hard for interop. But yeah, it's a binary protocol, lets you do lots of things at a time. And I guess as a good demo, let me close that. So here is a live test. Where's my Gopher tiles? OK, so this is served over HTTP2. As an example, if we look at HTTP1 with 200 milliseconds latency, you can see, you can imagine these are JavaScript files or CSS, but the browser can only keep 6 connections open to a server at a time, which is like a policy decision. It used to be 1, then it was 2, and now it's 6. And that's kind of how browsers have worked around HTTP1 over the time. They're like, oh, I don't know, we'll just open more connections. But I mean, it still kind of sucks, especially at like 1 second latency. If you're out in the woods and you have a satellite internet connection, this is how you browse the web. On the other hand, if we look at HTTP2 with 1 second latency, like it was 1 second for all of them, but we asked for all tiles all at once. So that is the promise of HTTP2. But back to slides. So yeah, there wasn't really any improvement from 99 to 2013. They just kind of upped the number of connections. HTTP 1.1 in theory supports pipelining, where you could, on one TCP connection, ask for a whole bunch of things. And you have to get them back in order still. But in practice, it just doesn't work. And all browsers have it turned off. And servers don't really support it. And people in the middle, transparent proxies that try to like cache your stuff and help you out, they just choke on it. So no one uses it. So around 2009 or so, or probably earlier, Google had a browser at this point, and has some servers, and so Google started opting into both sides to like upgrade to a different protocol, which is pretty easy over HTTPS because nobody in the middle can mess with you, because it's all encrypted. So what you do at that point, is cool. So they started upgrading people to experimental protocols and measuring lots of things. And it worked out really well. Other people liked it. Facebook and Twitter and other people liked it. Facebook ended up recommending to the IETF that it become the basis for HTTP2. Other people kind of agreed. Some people disagreed. But most people are generally happy with it now. HTTP2 is basically speedy with a bunch of tweaks. So back to this HTTP request, HTTP2 request. You can think of it like that. There's a little 9-byte header. It starts off with the frame length. So first there's 12 bytes. So this is 12 bytes of the payload. You always have 9 bytes. Then you have 1 byte that says what this sort of packet is, what this frame is. 1 means headers. And then you have 1 byte of bits that are bits specific to this frame. So this one says end stream, which means, so every basically HTTP request you make over one of these long-lived, like could be days TCP connections, has a unique stream ID. And so a headers request starts a new stream, and so it has stream ID 1, and the end stream bit says from my side, the client is done sending. For instance, this is a GET request. There's no post body attached to this. And end headers means this is the full extent of my headers, and I don't have a follow-up frame coming later that, like, you could in theory have like a gigabyte of HTTP request headers, and then they would have to be cut into multiple frames. In this case, it all fits in here. And there's the 12 bytes of the whole HTTP request, which is compressed with HPAC, which is a whole new compression format that is like an adjunct spec to HTTP2 that is just crazy town with lots of different things. There's static tables of all the common things. There's I have here somewhere HPAC. Yeah, so there's all these tables of like common HTTP things that you will see. So these get statically assigned numbers, really short variable encoded numbers. Then there's static Huffman tables for like Google did some analysis of all the traffic it sees on the web, and this is the smallest way to encode that the empirical data that's there. And so this is baked into the spec. And so once you do all this stuff, that represents like a whole one of those GET connection type browser. And this encoding is stateful. So if you have this one TCP connection open and you send a cookie that's like, a page long, and you send your user agent, which has all that crap in a user agent, you send that on the first request, and the subsequent request, it takes like a couple bits, because you just refer back to something you did in the past.
Is it part of the stream ID that you referred?
No. It has nothing to do with stream ID, but it has to do with the connection. Right. So once your TCP connection dies, like all your HPAC state goes away. Yeah, I said all this. It's a compression thing. So these are the HTTP2 frame types that are defined. The ones on the right are kind of optional ones that are hints from the browser, kind of, and hints from the server. But the main ones is data. This is stuff going up or stuff going down. Like a post body or a response to a GET. Headers is, like a new stream, a new HTTP request. Continuation is kind of a hack in the spec that says, whoops, it didn't fit in a packet. I'm going to have to add another one on. These ones are kind of special in that all the other frames can be interleaved on the connection, but whenever there's a header that doesn't have the end headers bit set, you have to have a continuation directly adjacent to it on the wire. So yeah, of course, there's little special cases already. Settings lets the two peers, the client and the server, negotiate, like upgrade to like higher settings and say, what your flow control rates are, and maximum size of packets, maximum size of like various other headers, how big, you can make an HTTP request, stuff like that. Ping just lets the client or server say, hey, are you still there, or is this just an idle TCP connection that, went away? Go away allows for graceful shutdown. So in HTTP 1.1, you can have a problem where your Apache or whatever has a keep alive timeout of 30 seconds, and at 29.5 seconds, the browser's like, all right, here's a request, maybe here's the post. And at the same time, you have a TCP packet that's like, oh, reset coming this way, and the other one's like, here's my credit card details, and you don't know if the server got it or not. So HTTP2 actually addresses this in a clean way where you can know whether or not the server got it or the client got it, and so yeah, graceful shutdown on that. And window update is for everything in HTTP2 is flow controlled, so on every stream. So between the priority and the flow control, you kind of have a client that does a whole bunch of requests, but then the client knows, to render the HTML, maybe I need the JavaScript before the CSS, or I really want this file more than that one. So the client could tell the server exactly how much it's allowed to send on each one and how many bytes it's allowed. So the client can kind of, both sides really can control how the other one is sending crap. And it's a violation if you don't keep track of all these counters about how many bytes you're allowed to send on the whole connection, how many bytes you're allowed to send on a certain stream. So yeah, both sides have to do lots of accounting during the process. As far as how you upgrade from HTTP1 to HTTP2, with HTTPS, you do it with an extension in TLS. It was previously called NPN. Now they moved how it works. It's called ALPN, but it's basically the same. You basically just say in your handshake, by the way, after we're done with this whole little handshake business, these are the protocols that I would like to speak. And the other one says that too. So just like you negotiate your cipher suites and stuff, you can negotiate the protocol that you're going to speak next. And so then right after the handshake is done, you know. This works really well. Now there's this whole like political thing about whether all the HTTP goodness should also work for HTTP. And there's people saying, oh no, we're done. Like we have to encrypt everything on the web now. There's other people that say upgrading from HTTP doesn't even work in practice because there's all these transparent proxies that break everything, which is true. This has been measured. People counter-argue, but we could just tell them to fix it. But you don't really fix things on the internet. So anyway, in practice, for political reasons, as far as I can tell, there's support in the spec for upgrading from HTTP. But of IE, Firefox, and Google, and Chrome, and the Google servers, nobody's implementing this. I'm not planning on implementing this. No servers and no clients are really implementing it, but it's in the spec. So we will ignore that. Effectively, it's HTTPS only. Maybe with EFS Let's Encrypt thing, more people will have certs by default. But anyway, enough talking. Let's write code. So, how do I make big? I'll skip that. Big enough? Okay. So the first thing I did when I started writing this, I skipped one little part about the upgrading connections. You can see like this is what you have to do in a TLS thingy to accept a connection. You just make a TLS listener and you say the next protocol I'm going to support is H214, which is this is the identifier string for the protocols as HTTP2 draft 14. And then after the handshake, you look at the connection state, and this has a field called negotiated protocol. So anyway, so in there, there's a, well, I'll get to it later. So let's read some frames. So we want to read something and return something. We probably want to return a frame. We don't really know exactly what the frame is yet. I showed you the frame format. So there's 9 bytes. There's 3 bytes of length, a type, a flags, and a stream identifier, only the lower 31 bits of which are the stream identifier. Then there's a reserve bit maybe for use in the future. So the first thing I did was made a frame header struct and to represent that 9-byte header. And so there's the type, which is defined as just a named type over a byte. And then there's the flags, which again is just a name for a byte. Then I have the length, which is a uint32, because Go doesn't have a uint24. But so this struct is a little bit bigger than 9 bytes, but whatever. And then the stream ID. The frame type, like I said, was just a byte, has proper documentation, all that. There's a bunch of constants. Notice I don't use iota here. Don't use iota when you're actually like implementing a spec that has defined numbers. Use iota when you just need your own set of numbers that's purely internal. So here, this is what the spec defines these numbers as. I give them, little names. I define string methods on frame type, which is, very useful when you're dealing with a binary protocol and some crap comes in and you need to like log it. It's nice to have it all stringify out. So if it has a name, I print out the name. If I don't know the name, I say unknown frame type and whatever number it is. Likewise, there's a type called flags for thing, and has little convenience methods on it like has. So I could say, does this thing have this bit? So then the code kind of reads nicer later, and I don't have to say like little bitwise operations all over the place, and it compiles to the same thing. Then I have all the flags that are defined for each frame. So like end stream on data and end stream on this, they happen to have the same number, but like in the spec they're different. So we have different constants here for them. Then of course I have a big map of which bits are defined for which frame type, for which flag bits. And that ends up stringifying really nicely. So when I see some debugging, I get some stringification out of it that says frame headers with these flags set, and maybe this bit 2 isn't known, but it still prints out, and the other ones are symbolically written in stream 1 and link 17. So yeah, this saves you a lot of time when you actually write good string methods on things. OK, so we're back to read frame. We have an IO reader, and we're going to return a frame, which we still don't know what it is yet. But first, before we read a frame, let's read just the frame header, when we do know what a frame header is. Constant, whatever. No one needs to see this, so it's lowercase. But yeah, there's 9 bytes in a frame header. And so your first implementation could look like something like this, where you have var buff, and you have frame header len bytes, so 9 bytes. And we read full it. Whenever you read a thing, it always has to have at least 9 bytes. So we'll read full. And once we have that thing, we could just return the frame header. And just unpack it, get the length, and mask off the reserve bit. We don't really care if it's high or low. But the thing you'll notice here is this read full, because this is doing an interface call through this, the escape analysis really can't tell, because it doesn't know what the implementation of reader is. Doesn't know whether it will escape. So this will be 9 bytes of garbage every time that this calls. So really, we want to kind of like reuse the buffer that we read the frame header into. So we don't want a function like this. We want to like provide it the memory to read into. So instead, you could write it like this, where the caller supplies the buffer to read the frame header into. So now this is being passed in, and we just say it has to be at least 9 bytes, and you'll make that a requirement. So this is actually the real implementation in the code. Of course, there's tests for it. Always write lots of tests. There's actually probably twice as much code in the Http2 package as there is in like the non-test code. So I started off with some kind of tests like this that I wrote up some manual things and just kind of verified it does approximately the right thing. OK, so back to read frame. We now have read frame header. We don't really have a buff yet, though, to pass to this thingy. So rather than just having a read frame function, this is probably a method on something else. So at this point, I make a framer. And the framer has a reader, and it has a little 9-byte buffer. So we can just reuse this 9-byte buffer every time when we read. Little constructor to make a new framer. That's about all that there's there. We're going to use this framer for reading and writing. So now we have a read frame method on framer, and it just reuses this little 9-byte buffer on the thing. And then some ... So what is frame? You could probably go either way, struct or interface. I may change it back to a struct at some point for garbagey reasons, but currently it's an interface. There's like 9 or 10 different frame types, and what they all have in common is they all have a method called header that returns the frame header. I'll talk about what invalidate does later. We basically want to let the caller, we want to reuse the memory for all the internal fields between things, so we don't like generate garbage as things are coming in. So we have the caller, when it's done with the frame, call invalidate. I'll show how that works. But anyway, so the frame header, in addition to like those fields I said before, we also added this unexported valid bit that basically says, does the caller own this or not? And if they don't, we will blow up later. So then we have methods on the frame header, on the pointer to the frame header called invalidate, which is part of the interface. So nobody else can implement this frame interface. It's only the 10 types in the package can implement it, because you do that trick of lowercase method names on things. And then there's this check valid method that just blows up. And this is useful for debugging to see if someone did something on the wrong Go routine, or somebody like didn't understand the lifetimes. So here's an example of one of the 10 frame types. There's the headers frame. I just embed the frame header, so I get the invalidate method embedded. And I have accessors on it, like the headers frame had those 12 bytes in that earlier thing that had the HPAC encoded stuff. So the higher level code want to get access to those. But it's going to be using memory. This byte slice points to memory that it doesn't own. The framer owns that until the person calls invalidate. So this I called check valid on here to see if the caller does indeed still own this frame. And if not, I blow up. Otherwise, I return them the slice. And then I have some convenience methods on the headers frame that have cuter names, like headers ended, rather than having the caller have to write f flags has flag headers ended. So it just makes the call sites a lot easier when I'm checking bits. OK, so now it kind of looks like this. We have the framer, and We have some optional stuff that's in the spec, like the max read size. A lot of stuff in HTTP spec. I can't say HTTP2. It's a tongue twister. They start at really low limits, like 16K or 64K and various table sizes. And the two sides, if they agree that they have enough memory or buffer space, they can negotiate higher. So there's this max read size constant, the buffer. And then I also have this function here called getReadBuff. So after we've read a frame and we know that there's going to be like 32K or a meg or something coming, we need a buffer to read the rest of it into. And so I pulled this out into a function so we could do different policies about like how we manage the memory for incoming stuff. Because we don't want to like have every idle connection. If you have a server that has like hundreds of thousands of connections, you don't want all of them, because most of those connections are going to be idle, especially with HTTP2. You're going to have lots of idle connections all the time. You don't want them all holding on to a little buffer just in case I need to read a meg later. You kind of want them to get that lazily when they really, really need it. And then that you want to like return it back to somebody else that actually needs it. So I pulled that onto a function. The default implementation just appends onto this thing, this read buff. So you don't really have to think about, unless you want to override the allocator, the default thing is just to put it on there. OK, so then I have a map of, from all the frame type, a frame parser. So I have, back in the frame header, or the read frame function, we read the frame header already. We know how big it is. We got the memory for it. And so now we have make a type called frame parser. This is internal detail that, given the payload, returns the actual final frame interface. And so then we have a map from all the types and we have this function called given a frame type, give me a frame parser. And if it's a known one, so like do I have push? During development, I only had like 3 or 4 of these. And I would just fall back to the parse unknown frame one, which just basically does nothing. And so this was good for debugging. I probably should change this from not being a map lookup here every time and just do an array lookup and fall back to parse unknown frame. But so now read frame looks like this. We read the frame header. And if the length is bigger than we've negotiated is acceptable, we blow up and tell them the frame is too large. Otherwise, we get an appropriate buffer to read the payload into. Read full, and now we have the full packet, basically the whole frame in memory. And now we tell the type frame parser, which is knows the HTTP2 level details of like how to look at the bytes in there, what to do with it, and it returns a frame. And we also keep track of the last frame we read, and at the beginning of a frame we invalidate the previous one if there was one. So here's an example of one of the 10, like a parse a data frame. The spec says that if the stream ID is 0, because the data frame must be associated with a stream. It's not like some of the frames are like high-level things like negotiating settings, but data frames in particular are always associated with a stream. So if we see one that's like 0, we just drop the connection. They violated the spec. And so I kind of quote the spec in lots of these places and say what section the spec said this, and we have tons of tests for it all. One of the bits is flag data padded, which lets the clients obscure the size of their packets by putting in dummy data that isn't actually there. And so read all this stuff, keep track of what the actual real data is, ignoring the padding, and then return that frame. So there's 10 of these little functions that parse the different frame types. There's another file that has the errors, have a little error code, have all the error codes from the spec, and then there's the HTTP H2, I'll call it H2 spec, defines connection error and stream error. Connection error, you basically kill the whole connection. They violated the whole protocol, basically. And then there's a stream error, which means there was some problem specific to a stream, but we can recover, and only that stream, only that HTTP request goes away. On the writing side, there's a whole bunch of write functions that are specific to the frame types we have to write, writing data, settings, pings, data, blah, 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 stuff. Here's like one that writes settings, takes a variadic settings thing, and we say start write with the flags. We don't, and whatever the other one is, go over the settings, write some fields, and then we say end write. Those things just look like, and here's settings act. This is a really simple write one. We start a write frame type from settings with that flag, and I think that was length. I don't even remember what that one is. So on the framer, there's write, and there's the buffer that we write into to like build up that little partial packet. Start write. That's the stream ID. Yeah, so the stream for settings, the stream ID is always 0 because those aren't specific to settings. But we write out the 9 bytes here with append. We leave 3 bytes there ready to fill in at the end after we're done writing the thing. And then in end write, we know how big the buffer is now, so we know the proper length. And just as a sanity check, if we wrote more than we can express in 3 bytes, we blow up and say the caller did something really dumb. And then we know the buffer's big enough for this, so I kind of just abuse append to like quickly put 3 bytes in there because I don't know, it works. And it avoids the bounds checks. When you do append like this, the compiler emits a check that do you have space for 3 things rather than saying for every one do you have space for it. So I'm sure it's not even a performance problem, but it's cute. And then we write the thing to whatever the writer is. So that's writing, and then there's these little convenience things for writing a byte or writing a uint16 or writing uint32. Here's the write data frame method. We basically say, we don't have support for padding right now because I'm not sure anyone really uses it, but one day I'll add it. The framer has support for doing illegal HTTP2 illegal things, just in case you want to test another person's implementation and send them garbage. And so I have actually used my unit test framework against other people's servers and stuff, just implementing the right hooks to bring up their servers and stuff. So yeah, if this is the end stream bool, we set that bit, and then we start a write with the right flags, put the data in there, and it's called end write. So all these write methods are pretty easy. So now writing the server itself. I showed upgrading HTTP2. You just say that and connection state, and you get a field, negotiated protocol. And then in the HTTP2 package, as of I think Go 1.3 or Go 1.2, there's this field on the server called TLS next proto. And probably you've never used it before because there's no purpose of using it. But this is an existing hook that's been there for like a year or so that says given the APN or NPN or ALPN or NPN identifier like H214, what should we do with that connection when we receive it? And the default, if this isn't defined, is the Go HTTP package just handles it. But if you put something in there, in this package, in the new package, there's this configure server function that sets it to, this is H214 or H2. And then we used to say, oh, we'll handle the con. So basically, we hijack the connection from the standard library. So if you actually go to use this, you don't change any of your code. All your HTTP handlers are still the same. You still call listen and serve TLS or whatever. And it just transparently speaks HTTP2 when it can. So inside this package, we now have the other HTTP server, which has all the configuration that you've set. We have the actual connection, which is in practice will be the TLS.con. And we have the handler that you wanted to run. So for every connection that we get, we're basically going to have 3 Go routines, or 4 or 5 Go routines. But the 3 main ones is there's one that I call serve. And this one is non-blocking. It keeps all the state, all this accounting of flow control and stuff is in its maps and stuff there. And then there's one Go routine that's reading, and it's just sitting there blocked forever, basically, calling read frame header. We're just waiting for 9 bytes to show up. And once it gets 9 bytes, and then it reads the rest of the bytes, and it has a full frame in memory, then it sends it over a channel to the serve one and says, yo, deal with this frame. And then it sits there bored until it's been handled, and then we say, OK, read another frame for me. We unblock you. Likewise, there's a Go routine that's writing to the network, and it could block sometimes. It has to flush something. And but we never want to either block reading or block writing. We want this one to always be fast and non-blocking. And this Go routine, I had this one running all the time, but Go routines used to be 4K, then 8K, and then in the last release they're 2K. But still, that would be 6K of memory per idle connection, which is kind of a waste if you have, you want hundreds of thousands of connections or something. So I actually found it was faster to start up this Go routine to write a single packet and just let it be destroyed when it was done than sending a message over a channel, writing it, and sending a message back that I was done. So actually, every frame write is a new Go routine. And it sounds kind of ridiculous, creating so many Go routines so quickly, but Go's really fine with it. It doesn't matter at all. So your Go routine counts in your servers, if you look at your debug statistics, will be really high, but it's fast. So I think I can even make this the logic Go routine shut down most of the time when there's no packet to be read. That 2K will go away, and then you'll just, for every idle connection, you'll have this 2K reader one. And when a new packet comes in, if the the logic Go routine isn't running, we'll start it up, and it coordinates all the other stuff. So whenever a request comes in and it decides to make a new HTTP request comes in, we start up a new Go routine for your HTTP handler, which might be your default serve mux or your HTTP handler func, and they communicate with the serve one about like, okay, write some data, read some data, and all the pushback of like, you're not allowed to write, you don't have the flow control tokens to write this net, are all, this pushback happens on channels here. So I'll go through some code that shows some of that stuff. So this is a beautiful struct that is created every time you get a connection. There's just like craplets of channels that of things going up and down and sideways between all these little pieces. And we initialize the flow control with the initial number of tokens you're allowed. We set up the HPAC encoder and decoder with the buffer that we're going to write to and where we read from. What we do when we get a new header field, a new key value pair in the headers, which basically notifies the server that the connection that adds it to a list. And we build a framer, set the read size based on like whatever's been negotiated in the protocol, and then we serve. The serving one sets up a bunch of stuff. Basically, the first thing it does is writes a frame to the remote side and says, here is my policy on what you're allowed to do, like what your max frame size, max concurrent stream, so like how many HTTP requests can you have in flight at once. But then there's also all these defers that just, when the serve function returns, we tear down the world. We tear down all these other Go routines that are running, and we make sure any HTTP handlers that are blocked get unblocked, because you don't want a handler sitting around blocked on a write or something. It's trying to write data on the HTTP response writer, but then the remote side had killed their machine or closed their connection. So you want to unblock those too. So all these things kind of just tear down things.
Is it the write frame that creates a Go routine every time?
Yeah. Right. Well, write frame does via a write scheduler that I'll show in a second. Yeah. Yeah. So and then this is the bottom of this first function of serve. Then basically all it is this big for select loop that waits for things to happen, like a frame coming in or a notification from the write Go routine that we wrote a frame. So then we note, okay, we're no longer writing a frame. Now we can schedule another frame write from the frame scheduler. Because HTTP2 has all these prioritization things. The client can say, I want JavaScript before CSS, and I want all this. And so we may have all this stuff kind of buffered up, ready to send them, but we don't know which packet the client wants next. So they're all sitting there in memory, or some maximum bounded size is sitting there in memory, and we choose what to send them next. And then there's other things like they didn't send their settings frame within the right amount of time, so then we go away. This is some shutdown stuff. This is the Go routine that sits there reading all the time. Basically, it makes a little gate. I have on this side, I have a gate, which is just a fancy name for a channel of empty structs. And then just so I can attach some names to it, so I don't have to write g send struct curly 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 curly. And I can just say done and wait. And so I make this gate. I read the frame. I send it to the serve loop. It says, hey, I got a frame, and here's a gate. And so when you're done with this frame, let me know. It just sits there and calls wait, and expects so. This pauses the Go routine so it doesn't trample over the memory that somebody else is already dealing with. That's the frame and gate. Nothing fancy there. It's the interface value and the channel. So I know Go routines don't have IDs, and we don't ever want to give you IDs because you'll do gross and disgusting things with them. But it is possible to get at them, and sometimes it's useful. Andrew's probably angry at me for even showing the slide. But so I found, there's these 3 Go routines, or 4 Go routines going on. Your HTTP handler, the serve one, the read one, and the write one. And you have all the state, all the stuff on the server connection thing. And it's easy to document in English what the rules for access is. Like, this one can only be done, this data is owned by this Go routine, this data is owned by this mutex, or guarded by this mutex. But enforcing it, the race detector works very well when you actually trigger a race, but it doesn't catch something that you did wrong, but you got lucky. So I wanted a little bit more paranoia. So I made this type called Go routine lock, which is just a uint64, the size of internally a Go routine ID. and I made a little constructor that looks up the current Go routine ID using undisclosed hacks, but you can look in the code. It's really, really slow, so it's only run during tests. And then I say, then I have check, and I have check not on. And basically, this creates a little number that when you call check on it, the number better be the same damn Go routine that when you originally constructed this thing, otherwise it just blows up. And so during tests, I set debug Go routines to true, and in production, these are like no ops. But so then I think I showed that on this page. Yeah, I have things like in serve, there's like servg.check. And so most of the functions in this all start with like what Go routine they're locked onto, and it's just a check. And this I've caught me 3 or 4 times, but those are 3 or 4 times that would have taken like days or weeks to debug. So yeah, so I have things like write frame handler that has documentation about like what Go routine you have to be on. And there's methods here like check that you're not on the serve Go routine to call this one, or write frame, check that you are on this Go routine to call that one. So this depends on whether or not it's a handler trying to write something or a frame write that's happening from the main logic loop, the serve loop. And when we do want to send something, we basically just add it to the frame scheduler and say, hey, enqueue this, maybe not right now, and then we schedule a frame write. The frame writer says, if we're already writing a frame, and the frame writer always runs on the logic Go routine, the serve loop, and we say if we're already writing a frame, well, we can only write one at a time, so do nothing. We'll get tickled again later to run and schedule something else whenever that frame is done writing. Then some stuff like, oh, if we need to tell the peer to shut down for during graceful shutdown, we send that. If we need to send the settings act, we'll do that. Otherwise, the main case is we ask the frame scheduler, hey, what's the next best thing to send? And this does the prioritization of various things. And if we got one, then we call start frame write. And start frame write actually does the writing. There we go. Where did my slides go? Scheduling. Well, okay, that's all about there for now. Anyway, so then there's what's this stuff like process frame. This is why I organize lots of the other ones. When a frame comes in, there's basically just functions for dealing with each one of the ones. When you get like process headers, we check all the stuff in the spec, like is this what? Font? Better? Verify that the stream ID is in the right range. The stream IDs always have to be odd in one direction and even in the other direction because either side can initiate streams. The server can push preempt. I didn't talk about this, but in HTTP2, the server can preemptively issue a response for an HTTP request that hasn't been made yet. So if you get a request for the slash, so your front page, you know that there's some CSS and JavaScript or something on the page. So you can send the response for the front page and say, here's a hypothetical request for you that you can use if you want, and here's the answer to it. And so then the client can get all that at once in one stream without another round trip. And so because both sides can generate IDs, one side has to be even and one side has to be odd. So on the server, we check that it's actually odd. We make sure that they're not reusing a stream that was old or in the wrong state. But then we create a stream for it with the ID that they said in the certain state. And then do the prioritization stuff, and then process those 12 bytes. Remember those 12 bytes that were HPAC compressed in that first ugly slide? Or it's a continuation, which is, I told you, like the same one as headers, but they have to appear back to back on the wire. So if so, we process a header block fragment, and we write it into the HPAC decoder. So these can come on any boundaries. You can have any arbitrary, like user agent, Mozilla 5.0, blah, blah, blah. That could be split over dozens of frames, and it's not aligned on key value boundaries at all. So you feed the HPAC decoder whatever data. Yeah, there's a lot of these to-dos where I'm reading the spec, and it doesn't say what you're supposed to do. So I think I filed 6 or 7 bugs against the spec that just says, what error code should I use in this case? I don't know. I guess that would be a stream error, but I haven't implemented that one. I think that would bubble up and be a connection error any error that I don't annotate as a connection error, stream error, becomes a connection error, and we kill the whole connection. But so yeah, call HPAC decoder write. At the top, when I made the HPAC new decoder, I specified a callback, and this is a method value. So on new this is the receiver name, and this is a method name. So the thing by itself is a function, and I'll go to on new header field. That type there, HPAC header field, is just a struct, basically a key value string. And then I could check, whether it's one of these magic ones. Rather than sending like get all capital and then a space and all this stuff, the method, the path, the scheme, the authority, these are all just magic key value pairs that start with colons, and nothing else can begin with colons. We also check things like cookies are special cased in the spec for weird reasons. We check that it's a valid one. You can't have any uppercase fields in HTTP2. So we normalize it in Go, so you don't see a difference in your HTTP handlers. But if on the wire we see a capitalized field, the spec says you have to hang up on them. So tests are fun. There's whole bunches of tests in here that do things like, so first I made a type called server tester, just so I could make the other test down below easier. And these have lots of little convenient methods for doing stuff. But then I'll have a test like, here's a single test that a post with no content length and end stream does the right thing. So here's an HTTP handler, and in my little server tester that gets passed into test server request, which is a little test helper, we write the headers with stream ID 1 and the block fragment with method post and this bit set and that bit set, and we verified that what Go sees eventually is a post with that thing. Content length can't be 0 because we didn't know, and so there's just pages of these of all the different little corner cases, and if you run it, you'll see like tons of little tests of all the different cases. And there's even one test in there that won't run on my laptop because I don't have boot to Docker, but actually. Yeah. Oh, OK. Questions? There's fun tests. We use Docker to run integration tests against other implementations. Yeah. The question is that Go routine lock, making it public in the standard library. I think actually I would make a case to others that it would be useful, but I expect pushback. So I'm not actually writing little 9-byte in separate packets. The frame scheduler has a field that needs flush, and once the frame scheduler has nothing else to say, it writes to a buff.io writer. And once there's nothing else to do, it sends a special type called flush frame writer that actually flushes it to the wire. So, you could, in theory, and it'd be a minor performance improvement. It's not worth the complexity. Yeah, I mean, there are a couple more copies here, but.
Is there a reason why you use a struct of anti-structs in your gating as opposed to like a channel with a bool?
Yeah. I could do lots of things. The problem with the bool is like it takes up some space, and it also it makes the caller think, what's magic about true? What's magic about false? There's nothing magic about either one of those. And also, I mean, I don't care about what?
Is there overhead in like defining a new empty struct?
No. No, that's free. And actually, there's fast paths for various things. Like if you have an empty struct, it goes into different scheduler frame, blah blah blah. So. I think it's easier to read is the main reason. I don't really care about the performance.
But also just close the channel, right?
Well, I can close the channel, but I do this multiple times. I reuse the same. In the frame writer, read frame. Yeah. So I create it once, the gate up there, and then I just resend the same one every time. Because I mean, channels aren't so small. They're like I don't know, 64 or 80 bytes or something like that for all their bookkeeping. So, one more question. Good one.
Available in 1.4, 1.5.
Is what? Oh, this in 1.1. So the spec, the HTTP2 spec upstream isn't blessed as official yet, and it's still sometimes changing a little. So we don't really want to put it in Go until it's done. And I haven't finished the client or started the client, so it'll probably be 1.6. But it's available, on GitHub, and you could add it to your thing in like 2 lines of code. I think you import and they say configure server. So we're using it in Camly Store. So. Yeah. I mean, once it goes into 1.6, it'll just be on. Like you won't have to do anything. So. Cool.
The server code is still the same, like the same response writer, request.
Yeah. The interface that you see is unchanged.
Okay.
There'll be some optional things that you could opt into to like do that server push thing.
I see.
But yeah. Cool. Thank you.